So example number 3. During takeoff, an airplane accelerates at a rate of positive 2.5 meters per second squared. If the plane starts from rest, how long does it take to reach its takeoff speed of positive 175 meters per second? So, gonna take note, accelerates at a rate. So again, even though there's no, let's say for example, in some cases, they will try not to write accelerates here. Like an airplane moves at a rate of 2.5 meters per second. Well, since the unit is meters per second, that tells you that it is acceleration, okay? So in some problems, they might just say the airplane blah 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 at a rate of let's say 2.5 meters per second squared. So remember that from the unit itself, it tells you that this is acceleration. Okay, then the plane starts from rest. How long does it take to reach the takeoff speed of positive 175 meters per second? So again, I will always start with the given. So I should expect that in your solution, if it is a word problem, you should start to identify your given. Okay. A is plus 2.5 meters per second squared. And my initial velocity is, it starts from rest. So therefore it's 0. And the final velocity is positive 175 meters per second. And how long does it take to reach this particular speed? Well, t is a question mark. So again, if I'm gonna start with my formula here, delta t, I can also manipulate my equation to get Vf minus Vi over A. So again, if you're comfortable doing this one, yeah, that's fine. Like after manipulating your equation, that is where you start substituting the values. So 175 minus 0 all over the acceleration of positive 2.5. Okay? And again, automatically, since the units are in the units of what I want, like velocity must be in meters per second and the acceleration is in meters per second squared, automatically the unit of time here should be second also. So if I'm gonna solve for that, this should give me in 2 sig figs 7.0 times 10 to the power of 1 seconds. Okay, in 2 sig figs. Again, this is the purpose why sometimes you need to express them in scientific notation, just to explicitly express your answer in the right significant figures. So I will not write 70 seconds because 70 is just one significant digits or significant figures. Okay, are there any questions with this one?
How do we know that it's seconds and not seconds squared?
Uh, you can check that one by plugging in the units, but since I'm confident because of the units that was given to me, like we arrive meters per second squared, since if we go back to acceleration, it's delta v over delta t. So the unit of your delta v is meters per second over second. That's why you get meters per second squared. So that means that for the acceleration, we can get the units of meters per second squared if delta v is in meters per second and delta t is in second, right? So we can get meters per second squared if the unit of my delta v is meters per second, or at least the two velocities, the final and the initial, is in meters per second, and the time is in second. I get meters per second squared. So it also follows that if a is given in meters per second squared and velocity is in meters per second, automatically delta t is in second. Or if you want to check with that, we know that delta t from our expression here is just delta v over a. So if you want to work with the units, delta v is meters per second, and acceleration is meters per second, right? So therefore, you can take out this part here, meters per second. So what is left is 1 over 1 over second. But what is 1 over 1 over second? That is just second. So again, sometimes the usefulness of placing the units in your solution is that it's one way to check also if you're doing the right thing. Because if somehow your expression for the time here is wrong, like somehow you flip acceleration over delta v, the unit there would change. It's no longer second. So in a way, it will also check whether you're doing the right thing or somehow you did the manipulating of your equation wrong.